Before it starts, I just want to tell you the ball here represents the jumper.
Before jumping, the person is standing at rest on a surface, and there is no vertical or horizontal movement. The net force is 0. So to calculate the normal force, we use the equation F net y equals may. The net force is 0. We can rearrange the equation, which will give us 1.47 newtons.
So before jumping energy, it's basically just Eg equal mgh. And you plug in all the numbers we have, and you got Eg equal 1.05 joules.
While in free fall, the bungee cord is loose and is not providing any force of tension. In this situation, air resistance is negligible. There's only movement downward by the force of gravity. The acceleration downward is at 9.8 meters per second squared. Force of gravity is given by mg, or the mass multiplied by that value, which is 1.47 newtons.
Okay, so the free fall energy. Before we talk about the energy, I want to tell you something. As normal, we use equilibrium point as x equals 0. But for now, we are going vertically downward. The equilibrium point here is much longer than before it's stretched. So we call the string here the reference point. And right now, based on the law of the conservation of energy, we have Ek equal Eg, and Ek is at the reference point, and Eg is at the top of the system. And we have the formula here, and if you plug in the data here, you will get V equal 3.92 meter per second. And also, at the same time, you can find K, which is the spring constant, based on the formula F equal Kx. And during this time, we only have Fg exist on the spring. So Mg equal Kx. And x is 0.05. It's the distance from the reference point here to the equilibrium point. So, and finally, we can get K equal 29.4 Newton per meter.
At the equilibrium point, the rope is no longer loose, but it is not stretched, nor is it compressed. This point occurs at a split second. The force of gravity and the force of tension are equal, and there is no horizontal motion. In order to calculate the force of tension here, we again use the equation F net y equals may, because we are again working in the y-axis. We can rearrange the equation so that Ft is equal to Fg. Force of tension is equal to 1.47 newtons.
Reference point energy. And we have ET1 and ET2. They are equal based on the law of conservation of energy. So we have those elements here, and we add them together to make the equation. And we plug in the number, and you will get V equal 2.42 meters per second. And you get, based on this, you can get EK2 equal 0.4 joules. So EK2 equal ET2.
During the return trip back up, the person is traveling back up from the minimum point. Here the force of tension is greater than the force of gravity because the person is moving in the upwards direction. We can still use the equation F net y equals may to calculate the force of tension in this situation. However, the net force is not going to be 0.
Return trip energy. Those are the two graphs. First graph includes the terminal energy, which is the energy stop the ball at the end, and that one doesn't include it. So for that one, when the ball moves up and down, the gravitational potential energy and the elastic energy changes, and they balance out each other. As the ball moving, the terminal energy increases, and also the total energy doesn't change.
At the maximum amplitude, the person is not at the maximum height or starting position, but the same distance above the equilibrium point as they were below the equilibrium point when they were at the minimum. Both the force of tension and the force of gravity are equal, and additionally there is no horizontal motion. So we can again use the equation F net y equals may. Rearranging, we can find that Fg is equal to Ft, and then we can calculate the Ft in this situation, which will give us 1.47 newtons.
Highest point energy. So same graph as before. So what we want to find is ET1. EE and EG are the energy that we want to find right now. You just need to use the data that we have. They are the same. And to find total energy, you just add them together.
The person is at the lowest point that they will ever be during the entire bungee jump. So, to calculate the tension at this instant, we can again rearrange the equation so that the force of tension is equal to the force of gravity. We will find that the force of tension is equal to 1.47 newtons.
For the minimum point energy, because there is no air resistance and there's no thermal energy and the amplitude doesn't change, so all the things here and the answer for here are the exactly same as the highest point energy. This is a video of the real bungee jumping. Here, train goes straight down to the lake and go backwards. So those are the four main elements that might make the angle of the train in the real life.